All right, so in this video, we're going to be looking at several examples of doing line integrals by the definitions. And in order to understand how to do that, we're going to need to remember how to parameterize curves. So we're going to go through a couple of very quick examples to start with to remember how to parameterize curves, because it may have been a while since we've done that. If you're taking Calc 3 in a typical sequence, you might have done parameterization of curves back at the end of Calc 2, and now line integrals are coming up toward the end of Calc 3, and so it may have been many months since you've done any examples like this. So we'll just walk through these very quickly so that it's clear where we're getting all of our parameterized curves from. So if you're dealing with straight lines or line segments, this is sort of the most basic way of connecting 2 points. And there are certain cases where the actual path that you take to get from point A to point B doesn't matter, in which case you can just go by a straight line. So our example in 3 dimensions is going to be point A is the 0.159 and point B is -2,710, and we want to make the connection between, we want to follow the line segment from point A to point B. So first, we're going to calculate the vector that connects the 2 points. So the change in X, the change in Y, and the change in Z. So second point minus first point, there's a -3 change in X. 7 minus 5 is a 2-unit positive increase in Y. And 10 minus 9 is 1. That is a 1-unit positive increase in Z. So our vector that defines the direction that line is pointing in is -3, 2, 1. Now the path itself then will be that vector that we just found times t plus our starting point. Our starting point is the point A. And the advantage of this sequence is that when you start at t equals 0, you're on point A. And when you stop at t equals 1, you're at point B. So if we substitute in our A values and then distribute these component by component, -3t plus the first coordinate of our A point is 1, and then 2t plus the Y component of A is 2t plus 5, and then 1t plus the Z component would be t plus 9. And so this would be our R function that goes into our line integral. This is our parametrized curve for that line segment. Now, this would be the same thing as saying this in parametric form, but typically when we do line integrals, these are completely interchangeable. And again, the whole advantage of this is that now we can go from point A to point B on the interval 0 to 1. Now, if you have to connect through several points, because there will be some problems where you have to go from point to point to point to point, you would just have to repeat this process for each consecutive pair of points. Now, in some cases, you will see examples, particularly in textbooks, where they will try to make the t's consecutive. And so one segment will be from 0 to 1, and then the next segment will be from 1 to 2, and the next segment will be from 2 to 3, and so forth. If you choose to do that, then on the next segment of the curve, simply replace t with t minus 1 for the interval 1 to 2. And if you're on the interval 2 to 3, replace t with t minus 2, and then follow the same procedures. Now, it turns out that when you're doing these integrations, you can do them segment by segment, and so you don't need to really make the t consecutive. You can always use the interval 0 to 1. But if you do need to make the t consecutive like this, then when you're setting up your equations, just remember that the default is 0 to 1. So if you're going from 1 to 2, use t minus 1. If you're going from 2 to 3, t minus 2, and so on. Now, for curves like circles and ellipses, in the parametrized version, we use cosine and sine. So for circles, we would have the radius on both of these A values would be the same. So we would have, for a circle of radius 2, for instance, you would have 2 cosine t and 2 sine t. If the center is at the origin, then h and k are 0. If the center is not at the origin, then you would simply add those center values to your sine and cosine functions. Now, in this case, the cosine in the x position will start at the positive x-axis and go counterclockwise. If you switch the sine and the cosine, then you will start at the positive y-axis and go clockwise. So pay attention to the way that the problem is worded. If they tell you to go clockwise, or if you're starting on the y-axis, then you may need to adjust this. By default in mathematics, if it's not specified, we're assumed to be starting at the positive x-axis and going counterclockwise. And so this would be the correct parametrization. But some problems will have you start in different positions or have you go in the opposite direction around the circle. And then again, you can do this, you can accomplish this in, at least in part, by just switching the sine and cosine. Now, if you're doing an ellipse, then again, centered at the origin, then the coefficients will be different, but the idea is basically the same. You would just have, again, the major axis would be larger, and that would be on whichever coordinate it is along the ellipse. If x is larger, then a will go here. If y is larger, then that would be equivalent to having a on the sine function in the y coordinate. But in general, whatever this relationship is, whichever one is larger or smaller, the one under x goes on cosine and the one under y goes on the sine. And then again, you can shift off the origin by adding constants if you need to shift away from the center at the origin. Now, for other curves, if they're giving you like a function like y equals x squared or something like that, then typically you would just replace x with t and then replace that t in your x equation for y. And so you would just have ti plus whatever your expression for y was in terms of t for the j component. Now, you don't really run into this very much in 3 dimensions, but you do in the 2-dimensional curves. And you could also solve other kinds of functions in this way. All right, so now let's go on to our line integrals. Now, there's a bunch of different notations for line integrals. Typically, you will see an integral sign with a c at the bottom and then some function of x and y times ds. Or in the 3-dimensional case, the same thing, but a function of x, y, and z times ds. If the function is, the curve is closed, so it starts and stops in the same place, you may have a circle through the integral sign, but that's just a notation to indicate that the curve is closed. It doesn't actually affect the way that we go about calculating it. Another common notation for line integrals is this integral of f dot dr, where f and r are both vectors. And again, the c is just along some curve that we then have to parameterize and put in our definite limits for. We may also end up with things that look like this. So we have mxy dx and nxy dy, or in 3 dimensions, mxyz dx, nxyz dy, and pxyz dz. Now, these 2 notations turn out to be actually equivalent to each other. One is just sort of a differential notation. This is more like what you would see typically in a work problem. But these are all equivalent to each other. The procedures for going about and solving them are a little bit different, but they are fundamentally, particularly these last 2 examples, are basically just rewritten versions, and so a lot of the steps are the same. The one that is sort of standout is the ds one. Now, so let's go through some examples. So first, we're going to evaluate this line integral on the curve given by, now in this case, they've given us the curve, so we don't have to create our own parameterization, and they've given us the interval on which to apply it. Now, in order to actually do this integration, we need to find a couple of things. So the first thing is we need this to be a function of one variable because we have only one integral to work with. So what we're going to do is, since we're following along this curve, we are going to replace our x, y, and z expression in terms of our curve expressions. So x will be 12t, y will become 5t, z will become 84t. And then when we plug all of that in, we end up with 10,080t cubed, when we multiply all the coefficients together. Now, for this kind of an expression, the ds part of the equation is essentially the arc length of the curve. So it's the magnitude of r prime of t dt. So we're going to calculate that next. So the derivative of our function, the derivative of 12t is 12, the derivative of 5t is 5, the derivative of 84t is 84, and then we take the square root of each of our components squared. In this case, we get a nice whole number. The square root of 7225 turns out to be 85. Now, sometimes, of course, depending on the kind of function that you have, this was just a straight line, but you may get functions of t under the integral, under the square root, that may complicate your integration, but fundamentally, it doesn't really change the nature of the problem. We take our ds and we replace r prime of t dt with 85 dt. 85 times the 10,080 is 856,800, and then we just integrate t cubed from 0 to 1. And when we do that, we end up with 214,200. All right, so in our next example, we're going to integrate along the closed curve cosine t sine t 4t on the interval 0 to 2 pi. So this is a circle at the height z equals 4. And so before the parameterization of the function in terms of t, we're going to take our function here, and that is expressed as xy. And so we're going to replace x with cosine and y with sine. So we're going to get cosine t sine t. And then we're going to take the derivative of our r function because we need the ds, and ds is the magnitude of r prime of t dt. So we're going to take our derivative minus sine ti cosine t j. The 4 drops out because it's constant. The magnitude is then sine squared plus cosine squared, which we know is 1. And so then this goes into our line integral. This was our f function. Our ds is 1 dt. And then we're integrating from 0 to 2 pi. And this is a straight up substitution with sine as equal to u. Cosine t is our du. So this becomes 1/2 u squared, or 1/2 sine squared, from 0 to 2 pi, and we get 0. Now, not all line integrals on closed curves will be 0, but they all will be 0 if the function we are integrating is the gradient of a potential function. In other words, if the field is conservative. But all you can integrate, and then you find out on the other side. Now, here's another example using the f.dr notation. So in this case, we're not given a function, we're given a vector field. So that's why the arrow is above the f. So this is representing a vector field, and you can see from the format that the field is x, y, and z, yes, but it's given in terms of I, j, and k. Now, in order to do this one, we are going to have our curve. The dr is the derivative of our function. So we're going to take the derivative of our curve, and then we are going to substitute into our f function our curve replacements for x, y, and z. So again, similar to our previous function, but now with a vector field. And then the difference will be, instead of calculating the magnitude of this in order to multiply by a one-dimensional function, we are going to dot our prime with our field. So let's walk through the steps. So here we're going to first take the derivative of our curve. So 2 cosine t minus 2 sine t and t. And then in the F field, we're going to take our curve and make this replacement. So before we had x squared, and we're replacing it with 2x with 2 sine t. So that becomes 4 sine squared t. We had 2 cosine t for y. Our field is y squared. So 4 cosine squared t. And then our 1/2 t squared for z gets replaced in our field for z squared, 1/4 t to the 4th. Now we're going to dot our two vectors together. So this is our field for f with just as a function of t. And then this is our original, or sorry, this is our derivative that we took of the curve. So the r prime of t. And when we dot these together, we get 2 times 4 is 8 sine squared t cosine t. And this one times that one is 8 cosine squared sine t. And then 1/4 t to the 4th times t is 1/4 t to the 5th. And this is now just a one-dimensional function. And now we can go ahead and integrate it. Now, this particular case, we would have to do for this term, and we're integrating over 0 to pi because our curve was defined here as going from 0 to pi. Now, if we were to integrate this, sine would be our u in this term, cosine would be our du, and then we would integrate that to be sine cubed. The reverse would be true here. So cosine would be the u in the second term, and negative sine would be the derivative for the negative sine t. So we would get cosine cubed again, so 8/3 sine cubed and 8/3 cosine cubed. The sign would flip to a positive, and then this will become t to the 6th and 1/24, and then we plug in our 0 and pi, and we get a crazy expression that amounts to approximately 34.72. Although you could express it in terms of pi and whatever you get, pi to the 6th and stuff. Now, in this example, this is the differential notation. So we're going to evaluate that. And this is, again, going to work somewhat similarly. We're essentially treating this as pre-dotted in the sense that 2x minus y is like the x component of our field, and x plus 3y is like the y component of our field, and dx and dy will get replaced from the x prime component of our r prime vector, and dy will be the y component of our r prime vector, so the y prime component. Now, on this particular example, we're doing several paths. So we're going from 0, 0 to 0, -3, and then we're going from there to 2, -3. So we're going to calculate them separately and then add the corresponding results. So in the first section of the path, we're connecting 0, -3, the origin to 0, -3. So again, you're doing your differences, 0, 0, that doesn't change anything, but -3 minus 0 is going to give you a change of -3 in the y direction. Our component then is -3t plus the starting point, which is 0. And again, this parametrized line segment is valid from 0 to 1 on these 2 points. So the variable x is always 0. So that's going to simplify our expression. If we go back to our integral, this is always 0, and this is always 0. And moreover, when you take the derivative of 0, you're going to get dx is also 0. And so the only thing you end up having to worry about is the 3y dy. And then the dy is the derivative of this, which is where the -3 dt comes from. And we're replacing y with the -3 in our expression. So we end up with 27t integrated from 0 to 1. And so you end up with 27/2. Now, in the second part of the path, we're connecting the point to, where are we stopping? To -3. So the -3 is not changing. The only thing that's changing is the 2. So the vector connecting them is 2, 0. So we're starting in the I component at 0, and then we're going to 2. So 2t plus 0 is 2t. But the -3 component is staying the same. So that's our starting point. We're just staying on -3. Now the derivative of a constant is 0. So that that dy component of our original integral, this is going to disappear because we're going to multiply by 0 here. So all that's gone. But then we're going to substitute our x for 2t and our y for -3. So that's our 2t times the 2 minus the -3. And then we're going to multiply the whole thing by the derivative of this, the dx, which is 2. And then we just do the algebra and complete the arithmetic. Once you have the value of your second integral, you add it to the value of your first integral, and then that gets you the value of the entire line integral. And notice that I just integrated these separately from 0 to 1. You don't have to do that 1 to 2 thing that we talked about earlier that you will sometimes see doing. That just makes the math harder. And so I don't bother doing that. You just do it from 0 to 1 on both integrals, and then you add the results. The time is not going to affect the value if you change your limits of integration. You're actually just setting them up as a shift. And so that's not going to affect the outcome in any way.